All right, so we're going to start with our next panel. So fireside chat. We don't have a fire here. Be nice though, it's cold out. So I'm going to introduce Matt Molchano and Sridhar Sistu. So please come up. So let's start with you, Sridhar. So you're a senior software engineer, you're a senior software product executive and leader, extensive experience in product strategy, cloud, architecture, DevOps, and large-scale deployments. So pretty much end-to-end, sounds like. And you are currently VP of AI offers at Schneider Electric. And you're currently working on accelerating AI adoption, which plays right into our topic today, which is delivering the state of the art. So, I'm going to ask you to give your remarks, but let me also introduce Matt before we go in. And so Matt, you're VP of software at Boston Dynamics. I've seen every single YouTube video of your dancing robots, so that's always fun. And you have over almost 20 years of experience as a technical contributor and leader. And you've worked on pretty much everything, all of those robots, right? Spot, Big Dog, LS3, Sandfly. And Matt has led efforts in product autonomy, software development, the whole end-to-end. So Sridhar, let's start with you. Go ahead, give your opening remarks. So we're going to have both of our guests give opening remarks, and then we're going to go into a conversation. And like I promised in the beginning, you raise your hands, and we can have your questions answered as we continue to talk.
Sure.
Okay.
Okay. Thank you. And I'm super happy to sit next to someone who worked on the spot, whose videos I showed to my kids, and I'm afraid I really cannot beat that. And I'm from an industry where things don't really move much. These are all like long-lived fixed assets in the field. But what is interesting about the domain that I work in is this is one of the most important topics of our times, which is energy and sustainability. And we see AI adoption, AI as a critical technology to support this, especially as we get into more and more on the electricity. And a lot of these things play into, the topic here, which is on the, computer vision. Of course, we have a broad, approach about adopting AI at scale. A key element of which is, how to use vision in many areas. And our, the way we look at application of computer vision is in multiple domains, which is a very classic case in manufacturing, where we have a tremendous opportunity for computer vision. And the second one is in customer interactions. Customer interactions even today, are largely unstructured. Whether you are dealing with, and I use the term customers, maybe partners too, even if you are dealing with vendors. And we see a lot of potential for computer vision in streamlining these unstructured interactions, that would have taken, people, a lot of time and effort to do that. So I'll stop here and turn it to Matthew, and we can dive deeper into some of the use cases of applying, AI.
Hey, great to share stage with you, by the way. So, at Boston Dynamics, we are not an ML company. We're not even really a computer vision company or a robotics company. Both computer vision and ML play big roles in our products. And, we think that as we've been moving from the space of robots that walk and dance and move around into spaces of robots that manipulate and are part of, hopefully job sites in the world that all of us live in, we're finding that both of those topics are really relevant to the new technologies that we need to build. And we've been changing ourselves in many ways. We've always been very conservative early on, I would say, about our use of AI and ML techniques. And over time, we've opened up and done much more there. And so, you can see some of our latest products like Stretch and Spot have key AI components and ML components inside of them, along with what we think of as classic computer vision type work. So things like being able to recognize where you are, pose estimation, mapping. And we're really trying to fuse both of those together. And we think there are lots of interesting and really hard to solve problems if you come at it from the perspective of wanting to be a user of it and put it on a robot and sell it as a product. And one of the things we're hoping for is to have all of you come and help us figure out how to solve some of that. So yeah.
Exciting. So thank you for joining. So I think really the goal today is to figure out how do you deliver state of the art, right? Whether that's ML pipelines, whether that's CV, or the application space at the end of the robotics, right? So let's start with talking about the biggest challenges. Like, what is the long pole here? You can prototype, you can prototype code, you can prototype, create a quick pipeline, and anyone can today log into one of the online cloud-related backend MLs and put a few lines of Python and start generating. But what does it actually takes to deliver something at scale? So maybe Matt, why don't you say, because you actually have the application space there that you're building through.
Yeah, sure. So much of our early success at Boston Dynamics was built on a model of build it, break it, fix it. Right, so we'd take our robots, we'd build up a robot, we'd have it go do something, and something would break. A leg would fall off of it, or it would fall down, or maybe the software would crash somehow. And then we would very aggressively go after the root cause of whatever that problem was. Track it down to a line of code or a piece of the machine that wasn't correct. And in ML, we found that it's challenging to implement that model, right? Because the answer oftentimes isn't clear. That you can't be like, oh, it was this particular RELU unit that went wrong, right? You can't possibly do that. And so you often are instead faced with being able to be unsure about how to solve some of the, how to identify a root cause. And if you don't know what the root cause is, then you're not really sure that whatever action you took is going to fix the problem and make it go away. And so for all you know, it'll come back the next time. And so that's a thing that we are constantly trying to find ways to be able to retrain our ML to collect data from our systems so that we can grow the system alongside behaviors that we're implementing these sorts of build it, break it type loops on. And I think that's been a key challenge for us as we have built out there. The other challenge that we found is that we're kind of at heart rapid prototypers, and so it's natural for us to have an engineer come up with an idea and just go straight at it and try to put it on our machines and see how it works. And we found that over time, ML requires a tremendous support base, right? And as we've grown that support base, it went from having an engineer to having a group of people to needing to pull in our DevOps and ML Ops teams to stand up training pipelines and constantly having to sort of move forward. And that's also different for us relative to how the distance between being able to productize a piece of rapidly prototype software and being able to actually say, hey, we can do this detection so reliably that we can put it inside our product and offer it to a customer.
Okay. What about, why don't you, Sridhar, comment something on the back end for it, right? So when Matt, you just talked about, build it, test it, fix it, repeat. I'm guessing you're also scaling the infrastructure on the back end. So maybe, Sridhar, do you have any comments on how would you go about it? So let's say, and I'm just throwing you under the bus here to say, you were trying to recreate sort of that, or build a infrastructure for something where you have dancing robots, so you can get a lot of YouTube views, although that's not your final goal. How would you go ahead and build it?
So, I think in the from our perspective, the challenges of scaling or deploying the state of the art are two fundamental blocking points. One is, and it's not so much about the infrastructure per se in terms of the actual technology pieces that are there. It is the infrastructure in terms of tools, processes, right organization model to do that if you want to do it at scale. For example, when we have to deploy a model that helps our translating, invoices using computer vision. We operate in multiple countries, multiple languages, multiple formats. Now, it's a single problem, but has a lot of diversity associated with that. And scaling them across the globe, because again, there are different regions where this works, is a tremendous challenge. Keeping everything, up to date, by retraining models as things evolve, is much more complicated than one can imagine. It's a classic infrastructure problem, support organization, but it is the scale of doing things in languages, different regions is really something that we are working at. The second thing that I would also highlight is, and particularly focusing on the vision side, is data. Getting the data, managing the data, labeling the data to train them, especially when you have diversity in the problems that we solve, is another huge challenge. It's more importantly, a lot of problems that we deal with, they are unbalanced data sets. You don't find those many defects. You don't find those many anomalies because we design equipment not to have those things. Now, how do you simulate them? How do you simulate those behaviors so you can, use machine learning to detect those problems is another, difficult area.
That's a good point. So we've heard two things, right? Software side and the data side. So how about hardware? Is that a hindrance to scaling up, either of you?
You said hardware side?
Yeah, like do you need hardware to actually be able to build a scalable pipeline? Or can you just do software in the loop? Or maybe, well, software loop may require that. Maybe just do simulators. Like, what is the importance of hardware in this context?
For sure, hardware is an important element, especially for us in deploying it at the edge. We don't find as much challenge. Again, it could vary from industry to industry and company to company. We don't find as much challenge in the hardware when we have to build train models, etc. Yes, it's expensive. You have to use GPUs. It's cost money. But the real challenge is finding the right hardware at the edge level where we apply this. If you are in a factory, if you have to run it on a production line and you have to make inferences in real time there, you need to have the right hardware there. You could be working in really harsh conditions, whether in a glass factory or a mine where you might be applying this. It's quite different, there. So the hardware challenges are more on the edge from our perspective than on the cloud or at the training and development stage.
I'm really hoping you're going to disagree a little bit here.
Sure, I'll disagree. For us, the original challenge was just having a robot to move your algorithm through the world, right? Because we want to do things in the real world. And so in some sense, we've solved that challenge. We hope not just for us, but for others. And then, for ML, the secondary challenge is, of course, having some sort of computing substrate on the robot that's able to do that. And we've hopefully solved that also for some of our customers by selling a payload that contains, a modern ML accelerator. But because we're a hardware product company, right, we have sort of long timelines to decide, what's the next thing that goes into the robot we're building. In fact, we brought one of our hardware engineers today, and one of the things that he's working on right now is figuring out, what goes in the next generation of Boston Dynamics robots to accelerate ML, for example, right? What kind of compute do we need, and how do we balance that with things like the really restrictive battery life that a robot has? It's like a phone in that sense, only it needs to move around and do a bunch of physical things. And so that's been a real concern for us on the hardware front, both something that we've solved, which is having a robot, which is really convenient, and having a well-working perception system inside that robot, but also on how we keep that robot actively at the forefront of the technology that for example, people in this room are building and hopefully offering out soon.
Makes sense.
Matt didn't completely disagree. See, he said it's on the robot, which is the edge from my side.
Yeah, but we're getting there, right? No, I think the important point that I'm hearing from here is that it also depends on the application, right? So there is hardware that's at the infrastructure side, and that is building up your compute, whether that's data centers or whether that's sort of edge compute. And then there's the other side, whereas the application, if your application is actually robots that have to do these complex maneuvers, then you need a robot, whether, somewhere along the pipe. So I'm going to come back to that. I'm not done with that. But let me see if our esteemed participants today have any thoughts, any questions. Do we have another mic? If not, I'm going to steal one of yours. Let me have your mic. You guys can share. Yeah. So introduce yourself. I think I'm just adding these rules as we go. Your name, where you work, so that way it also helps people, virtually introduce to each other.
Hi, so my name is Yaniv. I'm a computer vision engineer with American Robotics here in Waltham. We are a drone company, and we are developing an analytical pipeline for computer vision. So my question, I wanted to press a bit more about this combination between the hardware part and software, and focus on how do you manage the differences in cadence between developing a hardware product and choosing different parts that go with it, for example, sensors and compute, and then a software that goes along with it, which is much, I guess, faster to develop and change.
Maybe it's in your wheelhouse, Matt, yeah?
So that's a great question, first off. You know, the short answer for us is we run joint schedules and we keep the teams working very closely together. And then oftentimes, you know, you rely on the software team to carry the product onward, though, you know, like as you slow down the hardware cycles, you know, it's expensive to send ECOs out to the factory and, you know, make another rev on the product, but we keep moving the product forward as well. I think that, you know, if you look at it, usually we try to do as tight of a loop as we can, and we attempt to, you know, build prototypes quickly to de-risk things. So for example, we're considering some changes to some underlying technology inside one of our robots just now. And one of the things we immediately did was pull a bunch of software engineers together with some electrical engineers and said, quick, let's build the simplest version of this we can and try it out and see that we can, you know, check off these sets of risks that we think would be part of it before we go ahead and commit to building the next round. And we sort of do that at every phase of our process, and you know, we're very lucky to have a really essentially a very large-scale hardware team alongside the software team, and they're both very used to working together, and so that's been the answer for us so far. You know, I don't know how applicable it is to others, but it's been working for us.
Any thoughts, Sridhar?
No, I think he answered. I'm you know.
Okay.
Yeah.
You're playing.
Nothing more to add.
All right, you're playing peacemaker. All right. Can you pass the mic there, please? Flip it on.
Hello. Yep. My name is Krishna. I'm a master's in AI student from Boston University. So before I started my master's, I was working on a startup that I wanted to build in the lines of manufacturing and inspection using computer vision. And there's tons of, you know, just jumping right at the problem. There was a lot of problems that I personally faced. So I wanted to understand your perspective of how, you know, when it comes to edge cases, how does it work? Like the whole pipeline of edge optics and computer vision aspect of it. So how do you look at it, or how does Schneider go about solving it? Because I couldn't figure out like a model where you have one edge, one optic, one camera, and it works for all. When you go into it, there's a couple of problem statements that hit you. And also, what is your perspective on what is the next, you know, how the industry on that particular lines is moving towards?
So on the edge side and the optics, we rely on you know, the third-party, you know, equipment that we have. We are not building our own equipment. You know, I think there is significant maturity in the quality of images, and like you said, it's not just one. You need to have multiples to be able to make accurate predictions. And our view is. It kind of ties into your second point, which is that, you know, where does this go next, right? So it's not just about having the right model for, you know, doing the inspection and quality, but it's the, you know, the integration into the overall process and integration into, and, you know, having the right feedback loop. And process control as the next step is what is essential. So we see this as a first step in saying that, okay, I can, you know, do an inspection on, you know, an object coming out at high speed. I can quickly detect it, and maybe I have, you know, a controller, a limit switch that kind of pushes on the side. So we just avoid the cost of shipping poor quality to customers, right? But then the next question is, based on this, how can we adjust the process parameters and, you know, identify, you know, ways to minimize these defects? I think that's really where the sweet spot is. For us, when we look at the quality, it is not so much about detecting. Of course, detection eliminates lots of waste on the factory floor. You have people, but it is that controlling the process to improve quality is where the real value is. And it also, plays in because, we provide tools that integrate the whole process, and inspection is really one element of the overall process, that we do. I think the cameras and the vision, more or less is getting commoditized. You really don't have a lot of value that you can gain from that. It is really the integration process that we see.
Can you quickly touch upon like how to scale some of these, computer vision softwares when it comes to inspection or?
Yeah, I think I wish there was a simple answer to that. But I think, we transfer learning, I think is, one of the areas that is really exciting because, we have mature models that are there, but every situation is different, every object. So, can I just put in, 20, 30 images of some defective items and can I make the model robust enough? So that's an area we are investing in, and I think that's one of the most promising areas to scale it, because there is no single Uber, computer vision model that can detect problems in everything, whether it is, in our case, breakers or, circuit boards or, other, equipment that we do.
All right. Yeah, I got you. I see a couple of hands raised.
On the mic, yeah.
Sorry, who was? So you and then you.
Hi, Madan Gopalsamy from Signify. Question to Matt. Well, we also apply computer vision, in our industry, and we have several positions we are hiring. Some of the problems that we have in hand are little complex. They require skill sets beyond object detection and segmentation. But when you look for talents, very often the talent comes to you with an experience of the simpler problems, but not much talent could be found that could work on problems like the mapping, like perception, and things like that. And when we trace back, of course, the root cause for that is, I think it's probably the democratization of computer vision was primarily on simpler problems by organizations like universities and big companies and ImageNet kind of competitions. But not much is done on complex problems like I just mentioned. So from Boston Dynamics point of view, a company who has been pioneering this field, what do you think the industry should do to train more talent towards problems that is beyond detection segmentation? There are several other complex problems that companies like us want to solve, but we don't find enough talent, or we don't find it easier for someone to learn about them.
Can you give an example of the complex problem?
Stereo vision, for example, you again don't find a lot of models out there, don't find a lot of talent that can handle this type of problems. Mapping, for example, perception, for example, reasoning what is in the vision, not beyond detection, and being able to making decisions, for example, is something. It's a complex problem that you don't find a lot of talent.
Yeah, that's a great question, and also I'm not sure I'm going to have an answer for that. Within Boston Dynamics, we've been very lucky to have people join who are experts in things like vision, and then rely on mentorship as a way to have people learn new techniques from them. I learned my computer vision skills from someone who helped mentor me, right? And I've watched other people join and help mentor others. That could be a model for education that we could consider in the world. I also think back to when I was younger, right, before I started building robotics, there wasn't really a FIRST Robotics. There wasn't, nearly the kind of concentration at the university I went to. There weren't even a lot of labs doing robotics at that time. And, I look now and there's much more of that, much easier access. You can go to schools in the Boston area that have undergraduate programs focused on it. And so my hope would be also that it just might be a bit of a phase delay, and we need just to let education catch up a bit. And, you'll find that the next generation of people are able to write Kalman filters coming right out of school, or answer whatever estimation problems you have. Within the org, we rely on mentorship and a lot of close collaboration.
You want to say something?
Yeah, if I may add one more point, I think this is, if I generalize, this problem, there is always going to be highly specialized use cases or needs in this domain that, you cannot find, talent in the market. And I think our approach to this is to look for partnerships, both academic as well as with companies that specialize in. There is always going to be something that is really unique to do, I don't know, in oil and gas industry, if you want to do some, inspections there. Partnerships.
All right. So we have time for just one last question before closing remarks.
Hello, there we go. Thank you both for attending. My name is Waleed. I'm at Untether AI. We make a chip, an ML accelerator, so Matt, point me to your hardware guy later. But my question for both of you is, we're talking about state of the art here. So if you had to pick one, gun to your head, you have to pick one. What is holding you back from this? What is holding back the state of the art more? Would you say it's the software, or is it the hardware? Go ahead.
For me, it's the software. Sorry to pop the bubble, but that's our strong belief that this is where there are a lot more advances to be made for us to deploy this, and it's a long journey. We are just at the beginning of this.
I think, there are fundamentally difficult problems still to be solved in the software, right? As someone mentioned functional safety over there earlier on, right? We kind of struggle to understand how you would build safe systems around machine learning, right? The world of autonomous cars, as we understand it, is sort of based on this model of let's go drive 1 million miles, maybe something published in a NIST paper or something. And that's a hard bar for people who aren't huge companies and don't have, sort of infinite resources, right? Like running your robot 1 million miles is a lot of work. And so, us finding solutions to these conceptual problems, right, and then building the hardware and software that lets us achieve those, I think really is, still the thing that's outstanding there. And, I talked to our head of ML before coming here, and he said essentially a very similar thing, that there are just so many questions still to be solved, and so much hype to get around in the sort of ML world to get at the real, sort of root hard problems. And that's the stuff that I think if we could just solve that, that's what's going to get us leaps and bounds forward.
I think that was a trick question. It's application specific, but what I would do is I'd throw a curveball and say I think it's data. There is a time factor to it, and any company that needs to be effective or competitive in this space needs to have a certain amount of data. This is not just the data sets that you do for verification. You need to have something specific to your application. So if you're not collecting that for the past 5 years or 10 years, or you haven't started yet, you should probably think about it. That's just my opinion. All right, so we're out of time. 10 seconds, any final thoughts? Or 15 maybe. 10 is too short.
Sure. I think we are at the beginning of a huge transformation and an exciting journey. Coming from the enterprise context, there is tremendous work to be done, tremendous benefits to be gained. So super pumped, super excited about taking this state of the art into industry.
Matt?
First off, just thanks for listening to us talk about this stuff. And secondly, we brought a couple engineers from our team. We'd love to have conversations with a bunch of you. So please don't be shy. And this is such a nice size to be able to meet people and a nice scale of conference to actually be able to interact. So we're hoping to have some really productive conversations. And thanks.
Yeah. Well, thank you, Matt and Sridhar. Appreciate your time.